So Interactions is a company that basically focuses on providing state-of-the-art conversational systems, which we call IVA, or Intelligent Virtual Assistants, specifically for customer care, for enterprise customer care. So when you call customer service, you don't get frustrated when you're talking to a machine, and you can basically talk like naturally about any issues. So for those of you who are not familiar with few-shot learning, don't worry. Hopefully at the end of this talk, you will have a lot more knowledge about it. And if you do, I hope that you learn at least something from some of my slides. But just in short, few-shot learning is a field of machine learning that focuses on efficient algorithms to learn. Very little data. So there are applications that don't have the luxury of having a lot of training data, a lot of labeled data, and that's a very costly process. So that's why this is becoming more and more important, especially in recent years. It has gained a lot of attention. And I'm going to start by talking a little bit about the motivation behind it and why it is important. And then later, I will give you a very high-level review of different algorithms and basically the thinking behind them. And finally, I will talk a little bit about what are the future research directions in this field. Okay, so I wanted to start my talk by showing you the results from this paper. I find it a very interesting paper that compares the way humans learn versus the way machines learn. And they basically wanted to answer the question, who learns faster? And spoiler alert, humans learn faster. And we already knew that, but they systematically showed this. So they designed these simple experiments in image processing. They created 3x3 basically input images, which includes 9 binary features. So each smaller square or pixel can be 0 or 1. And then they defined some rules, like diagonal rule, where you can see in the first row that basically means, does that input image include at least one diagonal line? And then each task also was just identifying if the unlabeled picture or unlabeled image satisfies one of these, actually satisfies the rule based on the training data. So they basically separately tested for each rule. And then for training, they just gave the subject a few training examples, and I will show that they incrementally increased those examples. And they basically had to, both machines and humans had to implicitly learn the rules through those input trainings. And then they tried to have a balanced number of negative and positive samples. You can see in the first row, for diagonal, on the right, we do have some negative examples of the rule. And these are the results. The way they designed, and I'm not showing, by the way, all the results. If you're interested, please do read the paper. I'm showing just 2 of the figures. The way they designed the experiment was they incrementally increased the training data, 5 at a time. So they started with just 5 training samples. And the main finding was that by only 5 samples, humans do much better than machine learning methods. And they tried 3 machine learning methods, decision tree, logistic regression, and MLP. And humans, for all of the rules consistently, had the accuracy of over 60% with just seeing 5 training examples. And then the performance of humans improved up to almost 20 samples or so for training, and after that kind of flattened. And then on the other side, machines, they slowly learned, but for some of those rules, the diagonal rule specifically that I'm not showing here, it actually surpasses the human performance after it sees a lot of training examples. However, machines are not consistent across rules, so it really depends on the complexity of the rule. And as you can see, for these rules at least, there is still a big gap. And then one thing I wanted to note is that for the numbers rule, which is just a simple task of identifying a fixed number of black squares in the input figure, which here was 5, and humans do a really good job, but as you can see, all of those machine learning algorithms completely fail, no matter how many input examples they see. So why did I spend a few of my minutes on this? Because it is really important to understand that from the beginning, the machine learning and artificial intelligence goal was to mimic how humans learn. And humans, we believe that we learn in a very efficient way. Why is that? Because we use our prior knowledge. When we want to learn a new skill, we use all the skills from the past to learn. We don't start from scratch. But a lot of these new methods, especially in the deep learning world, that has really had really good results, even as I said, if seeing enough training data, they do surpass human level performance. However, the shortcoming is that they do rely on a lot of training data. And then, of course, there are other things like inefficiency. They have something called overparameterization. There is a lot of redundancy. And then if you have very little data, what happens is that they're going to overfit. And of course, bias and other things that the first speaker also touched on. And then few-shot learning is going to be basically using a handful of examples to learn a task. And there is a debate over how many is few. Some people do say 10 or less, some people do 30. I have seen 64 or so, so it is kind of debatable. But for the sake of this talk, we're going to say 10 or less. And then you might hear something like 10-shot, 5-class classification. So shot here basically means one training example. So in a 10-shot, 5-class classification, for each class, you're going to have only 10 examples, which is a total of 50 examples. A quick note about conversational AI. I know that a lot of you are familiar with that. I just wanted to show different components of conversational AI here. As you know, it enables us, humans, to interact with machines in a natural way, using our speech or using text. And if the interface is a speech, usually, traditionally, speech recognition is used to convert that speech to text. And then one of the core components that I'm going to mostly focus on is the natural language understanding part. And that is the part that extracts the meaning from your words or from the text. And that is really important because human language could be very ambiguous. And then, again, as you might know, state-of-the-art language models and state-of-the-art, basically, NLU depends on actually two-step training of language models. One would be the pre-training process, which takes advantage of a lot of unsupervised data that is out there on the internet, and then in a self-supervised manner without any labeling required, they kind of mask part of the input and they try to guess that from the output. These language models, again, the first speaker also mentioned that they have large number of parameters. It goes up to billions of parameters. And the question is that, is it really necessary to have these many parameters? And then in the fine-tuning, of course, what this language model helps us with is something called embedding, which is giving us a kind of compact way to represent the input utterance, and then we can then use it for any task, like classification again, and then we can do a fine-tuning. Again, the question is, for this fine-tuning, if there is a lot of training data with labels, then it's going to be a good model. if we have only a few parameters, this model is going to be overfitting. And then, hopefully by now we know that few-shot learning is important, but why is it important in conversational AI? Because we do have a lot of relying on these virtual assistants, and then we want to have a way of very quickly expand them to new languages, new domains, and we don't want to rely on a lot of annotated data. And as you know, annotating data is a very costly process. And then another problem is that for data privacy issues, sometimes it might not be even possible. So here I'm going to talk a little bit not about specific algorithms, but about the thinking behind the few-shot learning algorithm. And again, we are trying to mimic how humans learn new skills. And as I talked about, prior knowledge is important. Any type of prior knowledge, auxiliary information. So there has been task description methods using expert knowledge. Even if we have a task that has lots of data and we can find a similar task to our new task that we want to learn with very little data, why not somehow use that similarity? And then the other thing is efficient algorithms. Those are generally called meta-learning algorithms. I will spend a couple of slides on those. And then diversify. So one thing is that if we don't have enough data to learn from, maybe we can use models that learn different things from the data. So if you have models that have complementary information, then you can combine those. And of course, human in the loop, there is another way. So you could have active learning or other ways to have combine human intelligence with the machine intelligence so you don't rely a lot on the training data. Now a little bit more on specific algorithms on natural language understanding for few-shot learning. And again, by no means this is a comprehensive list, or also all of these bullets somehow have some type of overlap with each other. So I just wanted to show you, because there is every day that you look at Google Scholar, there are new papers up there, some type of few-shot learning. So I don't want to say this is all the methods that you can find. But again, I tried to put together a list of the majority of the methods or the main methods that are being used in natural language understanding. I did talk about the large-scale pre-trained language models. And then data augmentation is something that has been used for years. It's just that you don't have the data, then let's find similar data in that noisy data lake that could be kind of close to what you're looking for, and you could use some type of semantic distance or any other way. And those have been proven to improve the performance of these few-shot learners. And then pattern-based approaches, those have gained a lot of also attention. We could kind of say prompt-based approaches with this language model. It's just that it's like a fill in the blank, and then you don't sometimes even, which is called zero-shot learning, not even having any training data. You just query that big language model, and whatever you are looking for, that would be that blank that your basically language model hopefully gives you the answer. And rule-based methods. So don't forget that sometimes the simplest ways are the best ways. Simple keyword spotting, or there has been these programmatic ways of finding simple rules from the data, which is called snorkel, I think. So that could be also something that is useful. Hybrid approaches, I talked about how human intelligence can be combined with machine learning. And meta-learning, I'm going to spend a little bit more time on, because it has been really gaining a lot of popularity lately. And still, it's not very clear what is called meta-learning. There is, again, some debate about it. Some people say that transfer learning and multitask learning are not meta-learning, and some people say they are. So it really doesn't matter like what the definition is, but I'm going to talk at least about the idea behind it. So put it really simple, meta-learning is learning to learn. But that's a really generic definition. What does that mean? One of the papers from a few years ago, I really like this definition. They have a very high-level definition of it. They say meta-learning basically means that you systematically try to observe and learn from how different machine learning algorithms learn from data. So that basically includes everything. Includes ensemble learning, includes multitask learning, and transfer learning. But again, in the context of DNN and practicality, people have kind of limited this meta-learning to examples that you have a new task, but then you do have a lot of other tasks that are in nature similar to your task. Basically, you assume that your new task is kind of chosen from the same distribution of the tasks as your training task. And those tasks are called training tasks. And then you try to kind of learn from those tasks, and I will explain that. Oh, and the motivation, of course, is again, we want to learn like humans, and humans do use how they learn to learn new skills. Although I'm working on natural language understanding, it is sometimes helpful to look at the examples from image processing world because it's easier to kind of interpret. And here I wanted to show you an example that the target task is to classify the picture of a bicycle from the picture of a flower. And for each of those, it's just a simple binary classification. For each of those classes, you only have 4 samples. And then on the other side, you have this big data set of lots of images of different animals or plants or objects. And then the way you design those training tasks for meta-learning is going to be similar to your target task. So it should include only 2 classes at a time, only 4 samples per training, and then you try to learn from that how to do your final task, which I will explain here. So here I'm showing this kind of new thinking of how meta-learning is different from transfer learning and multitask learning. So in meta-learning, you're sequentially learning. So task T1 to Tn, those are going to be your training tasks. And then you start by a model. Again, imagine it's a DNN model because it is mostly in the context of DNN. And then you start with that, and every time you're updating the parameters for each task going to the next one. But these tasks are really similar to your final target task, that is task T. And then transfer learning also learns in a sequential way, but the difference is that you only have 2 tasks there. Again, like the pre-training and fine-tuning, you have one model, and then you want to use it for a target task. So it's a source task and a target task. And they don't necessarily need to be like exactly from the same distribution. And then multitask learning is very different from these two. At multitask learning, your goal is to learn all of those tasks at the same time. And then if there are many tasks, those tasks T1 to Tn, it could get really complicated, but for meta-learning, it really doesn't matter. So here I want to give you a kind of a more exact example that I am more familiar with, something that I've been working on a lot, which is the customer care intelligent virtual assistant. And this is a real-world example of why we need few-shot learning. So we have these enterprises that are our customers, and they have these conversational systems, each customized to their needs, and it's working for them. Now we have this new client comes in, and they want a very different thing. So it could be we have verticals. There could be like from the same type of business, or they might be a completely new one. And the other thing is that they don't necessarily come with a lot of training data or any training data at all. So they say, and I'm again like just talking about intent classification because it's easier to understand. Let's say at the very beginning, answer to how may I help you? And the person starts to talk about the issues they have with the product or sales or something like that. And then it's basically the task is, what is the intent of that person? What do they want? And that's a very like open set of intents. It's a very difficult task. And they sometimes come in with saying, okay, these are 10 intents, these are 5, and these are things that are important for us. And there are some definitions. So what should we do? We can go back to humans, actually. We could use humans and create some of the examples. But that wouldn't be enough. So we use our database to kind of find similar examples. But again, that is tricky because sometimes you find things that are semantically close, but then the intent might change because there might be like a very specific intent they are looking for. So then there should be like another review process. So humans in the loop everywhere to improve the performance. However, we do use the data augmentation methods to kind of improve our model. And then the other thing that we do is using human in the loop in another way, because these few-shot models are not going to perform very well. So what we do is that when NLU model is not very confident, we are sending that utterance to a human to annotate in a real time. So we could kind of call it real-time active learning, because not only it helps to improve the performance, but now we are having annotated data for the data that we specifically picked because those are difficult and confusing for the NLU to understand. And now we can build better models. So I have about 5 minutes left and almost done. This is not changing. Okay. Technical difficulty again. So I can talk through the rest. Nope. Doesn't go back, doesn't go forward. Yes. So these are the final slides, and I don't want to go over by a lot. There are still challenges, a lot of challenges actually. I'm mentioning 2 of them. One is that you built this few-shot model, but then suppose you have a data-driven model with a lot of data. So you have n classes with lots of data. You built your model. The client comes in and says, I want these new classes. You build the few-shot model. How do you combine these? How do you combine these in a way that those classes with a lot more data, they don't dominate the results? And then something that is very important, we should really try to evaluate and benchmark things in a way that is reasonable. So there are so many papers, but they're on few-shot learning in NLU, but there is still not exactly a standard way of doing benchmarking and having like these standard benchmarks. Each paper has their own settings. So I won't have time to go like through all the details of this, but again, there are wrong assumptions. Like they do use these large data sets and they subsample from there. So they're basically assuming that the test and train have the same distribution. But then again, if it's a completely new task, how do we know the distribution of the data? So these are some of the things that we need to have in mind. And finally, I started my talk by comparing human performance to machines. Here is a more recent study specifically on the NLU. And in the previous slide, it's the reference number 5. And here they, for some natural language understanding tasks, again, I cannot go through, one is natural language inference, and the other one is kind of a sentiment analysis task. So they compare humans to machines. And as you can see, when you get to really large language models with billions of 175 billion with GPT-3, they do work pretty well on a simple task of, is a review negative or positive? But then when you have a natural language inference difficult task, you can see that you can't really do as well as humans with only 10 or even 20 or even 30 shots. So bear that in mind. The other thing is that you can see that the variance of the results. So again, you cannot have just one accuracy. You have to look at the variance of the results. And then conclusions, I won't spend time on it. It's just basically we talked about why few-shot learning is important, and then we still have a long way to go to be able to learn in a more efficient way. And thank you so much. And if you have any questions, we have a few minutes, hopefully, for questions.
Thank you. Thank you very much, Mahnoosh.